Hi, this is Richard C. I'm a math tutor here at Wyzant, and I'm answering a question submitted by a student. This student is beginning to start his or her class in calculus. In calculus, we can actually figure out the instantaneous velocity of a ball that's thrown up into the air. But without calculus, all we could do is estimate that. So before calculus was invented, this is what we were forced to do is make estimates, and that was all that could be done. And so this was a couple hundred years ago. But this is the equation of the distance of a ball at time t. The ball's thrown straight up into the air. And normally I would do a little sketch here, but I don't think it would help. I think what we should just do is go right into the algebra here, because this is all about algebra. So for average velocity, for average velocity, sorry, I have to move this stuff around a little bit. So average velocity is just the distance traveled over elapsed time. And the graph will look like this. Here's time. And here's the height of the ball, or distance. And it's going to be a parabola opening up. We don't really need to know anything. Don't need to know this, but it would be helpful, I think, if you could tie this back to the idea of slope. So this is the slope of a line. Okay, so what we're going to do is we're just going to find the distance at time 1. So that's going to be 1, t equals 1 at time 1. Y is going to be 80 minus 16, so that's going to be 80 minus 16 is going to be 64, and the t equals 1.5, and then we're going to go t equals 1.1, t equals 1.01, t equals 1.0001. So let's just go ahead and do this. And of course, I'm going to be doing it on my calculator now. $1.5. So it went 64 units, but after a second and a half, it had traveled 84. And let me just finish this out on the calculator. So 1.1 is 68.64. One point oh one 64.474784. And finally, the last one, 1.0001. That's going to be 64.0048. If we look at the average time, the average velocity between 1 and 1.5, which is this pair here, you can imagine a point here, 1, and then another point at 1.5. And we would connect these 2 points with what's called the secant line. In order to find the average velocity, it's going to be change in y over change in x. It's just going to be the same thing that we've always done in algebra. So it's 84. Minus 16 over 1.5 minus 1. So 84 minus 16, 68 divided by 0.5 is 136. And the units we're using here are feet per second. Okay, so that's the first one. The next one is we're moving a little closer to the starting point. So the starting point was 1 second in, and we found the velocity to 1.5 seconds. But what if we just move a little closer? And the next one would be 1.1 seconds, and then that would be yet another line here. Something like that. 1.1 second. And we're going to recalculate the slope for this one. So let me change colors here just to differentiate. So the first pair, and then the next pair would be these two, right? This pair. The speed is going to be, average speed, it's going to be 68.64 minus 64 all over 1.1 minus 1. 68.64 minus 64 equals, divided by 0.1, 46.4. The next one and the next one and the next one. So I don't want to bore you with all these, but this next one would be these two. And then there will be one more. And I'll just change colors again, and you can fill these in on your own. Be these two. Each time we're getting closer and closer to 1. Now this last one will do. So this is going to be 64 minus 64.0048 minus 64 all over 1.0001 minus 1. So that's going to be 0.0048 divided by 0.0001. That's going to give me 48. So we can guess, because we're getting closer and closer, this one is basically can't even see it. It's so small. This last purple one, there's just a little dot of purple up there. So we would guess, based on what we're seeing here, is we're getting closer and closer to 48. So it's 0.0048 divided by 0.0001. Yep. So that's we could keep going and make t even smaller and smaller, and we'd probably be getting closer to something less than 48, but it's not going to be tremendously different from 48. And so that's our best guess at this point. You can imagine, since we're thinking about instantaneous speed, clearly at time 0, the ball's not traveled anywhere yet, so it doesn't have any speed at time 0 or velocity. And then the ball's thrown, and you can imagine that the velocity here is going to be very high, but then the velocity is going to slow down, and eventually the ball's going to pass the vertex here of the parabola, and then it's going to head back down, so the velocity is going to pick up again, but the velocity is going to pick up in the negative. So the closer we get to this, I'm just pointing this out because it makes good sense that the velocity would be slower, say, in the neighborhood of 1 than it would be in the neighborhood of 1.5, because in 1.5 you're still rising, although this is not drawn to scale. So that's the answer to this, and this is really just getting you warmed up for the idea of the first derivative, which will give you the exact instantaneous velocity at t equals 1. Okay, so that's it for this one. I hope that helped. I'll see you guys next time. Bye-bye.